All right. Hello, everybody, and welcome to the second in our series of Green Bank Observatory 65th anniversary colloquium talks. Here we're exploring some of the great achievements made by the observatory since its formation back in 1957, as well as how these topics have gone on to shape the field of astronomy. My name is Jessie Bublitz, and I am a postdoctoral fellow here at the observatory. Over the course of this series, we will hear from experts in fields to which GBO telescopes and staff have made significant contributions, discussing both their history and the future role the observatory will play. It is my pleasure to introduce our speaker this week, Dr. Maura McLaughlin. Maura is an Everly Distinguished Professor of Physics and Astronomy at the West Virginia University, where she uses radio, X-ray, and gamma ray observations to study neutron stars. She's also chair of the Nanograv collaboration, which stands for the North American Nanohertz Observatory for Gravitational Waves, using pulsar timing to detect millisecond delays, a sign of disruption by gravitational waves. And if that wasn't enough, Maura also works with the Pulsar Science Collaboratory, which invites high school students and teachers to train and help on the analysis of GBT and Arecibo data in order to detect new pulsars. Today, she'll be talking with us about the advancement of pulsar research at the Green Bank Observatory, beginning with the pulsating radio source, or pulsar, detected at the center of the Crab Nebula using the 300-foot telescope back in 1968. Just 1 year after the very first pulsar discovery with UK's Interplanetary Scintillation Array by Jocelyn Bell. Since then, the science of pulsar timing has expanded to observatories across the globe, but remains a staple of research and outreach here with the GBT and soon the latest CHIME outrigger. So please, let's give a warm welcome to Dr. Karen Masters. And if you have any questions, please feel free to write them in the chat, after the talk, we will have time for you to raise your hands and ask questions. When you're ready, take it away, Maura.
Great. Thank you, Jessie. Just one small correction to your introduction. I am no longer chair of Nanograv, and it's probably my fault. I probably, it's on a webpage somewhere that hasn't been updated, but Scott Ransom is our current chair of Nanograv. Can you see my screen okay?
Yep, perfect.
Okay, great. Yeah, so thanks so much for inviting me. I'm super excited to be able to take part in the 65th celebrations. And as Jessie said, this talk is kind of going to be split into two bits. I'm going to do an overview of sort of like the history of pulsar science with Green Bank telescopes, starting with the 300-foot, the 140-foot, and then, of course, the GBT. It will, of course, be a little bit subjective. I can't cover every single thing that has ever happened with Green Bank. Then I'll move on to talking about the present of pulsar science, and I'm going to focus a lot on the work of Nanograv, just to give me a chance to talk a little bit about all the exciting stuff that's going on with our collaboration, and then I'll look to the future and new developments. Before I start, I just want to say thank you to all of you at Green Bank. Green Bank has been such a huge part of my personal scientific career. I don't think I'd be at WVU if it wasn't for Green Bank. Duncan and I came back in 2006. I can't believe it's been that long, and being close to Green Bank, I mean, that was the thing that brought us here. Fred Lowe actually recruited us to come to West Virginia, and it was being close to the GBT that made it very attractive. We've spent a lot of time there. We've raised our kids on the site. We've raised lots of pulsar astronomers on site, along with Sue Ann and the fantastic EPO staff with our Pulsar Search Collaboratory. And of course, Green Bank has been super supportive to the Nanograv collaboration, both through telescope time, hosting us for meetings, fantastic staff at Green Bank who've been so integral to Nanograv stuff. So thank you all. The first time I came to Green Bank was actually in 1996. I was a brand new graduate student. I came to use the 140-foot. I was Zavan Arzumani, and he was a postdoc at the time. And the SETI folks were there. That was really cool. I had never heard of SETI before. It was really eye-opening. I got totally lost in the woods. I went for a walk and I came back about 3 or 4 hours later and saw them, was quite worried. But I just fell in love with the site on that first trip, and I've just been such a fan of Green Bank ever since. So I'm thinking about this talk and sort of like what to highlight as far as past Green Bank accomplishments. I went to ADS and tried to do a search for like, pulsar papers with Green Bank instruments. There are big tildes in front of these numbers of pulsar papers and citations because it's really hard on ADS to, make sure you have the right combination of filters to get papers that mention Green Bank data. But this is sort of like, I think, a reasonable-ish number, something like 1,000 pulsar papers with Green Bank data. And by Green Bank data, I mean any telescope at the GBO since pulsars were discovered back in 1967. A whole lot of citations. If I search on, the pulsar papers that have been published with Green Bank telescopes and I list them by citation count, people really like measuring neutron star masses. Those have way more citations than any other Green Bank papers. Double pulsar stuff, like pulsar timing stuff, and then gravitational waves, searching for low frequency gravitational waves using the telescope. So I thought this would be fun. I just included this list of sort of the Green Bank pulsar greatest hits. But I mean, the GBT and the 140-foot and the 300-foot, they've all made amazing contributions really in every single area of pulsar science. There's no area of pulsar science that they've not had not only some impact, but a really important and critical impact. So I went through sort of, from the very first pulsar observations with Green Bank telescopes to now. I can't cover everything Green Bank has done, but it was really fun to kind of look through that list of papers on ADS and pull out what I think are the most impactful papers. Some of the papers I'll talk about aren't huge scientific results like the discovery of a new class of objects, but more like setting in motion a new way of analyzing data. And some of them, of course, are big discoveries that Green Bank telescopes have made. And I'll spend maybe 15, 20 minutes kind of on this, looking into the past bit. So as Jesse mentioned, Green Bank has played a really important role in pulsar astronomy right from the start. So we all know Jocelyn Bell discovered pulsars in 1967. There were lots of ideas about what they were, but nothing really conclusive. And it was actually at Green Bank that Stalin and Reifenstein used the 300-foot telescope. And by the way, whenever I talk about these results, I'm not going to list the telescope names, but I've got pictures of the telescopes in the upper right-hand corner. So that'll show telescopes that are associated with the different results I'll talk about. But Stalin and Reifenstein pointed at the Crab Nebula, and they showed that it was known that there were radio sources, like DC radio sources, and they were the first to detect pulses from these radio sources. And this plot here shows their results. This is frequency versus time. And you can see the dispersion delay, the lower frequency signals arriving later than the higher frequency signals due to free electrons in the interstellar medium. And you can see this delay for 2 pulsars. This is a longer period pulsar. And this is the Crab Pulsar over here. There's just one bright pulse. We now would call this a giant pulse, a really bright single pulse. So this was a really important result. And so Green Bank observations were responsible for showing that supernovae cause pulsars. They result in neutron stars and pulsars. And this was a very important result, obviously, for our understanding of what pulsars are. As I go through, I've listed the number of citations these different papers had just for fun in case anybody is curious, although I haven't really these are not sorted in order of citations. I'm just going through chronologically. And then, after pulsars were discovered in 1967, after we, associated them with supernovae, Green Bank observations were really important, for the next decade or so, in trying to figure out what pulsars are, how they emit, and laying the groundwork for all of the fundamental physics that we can do with pulsars. So this is a paper that I highlight. This is from 1972. This was a paper by Dick Manchester, and actually 2 kind of related papers. And he looked at 21 pulsars. This is an example of 2 pulsars. You can see the total intensity here and the linear polarization. this plot shows the fractional polarization, and this is the position angle. These observations were really important, right? So knowing that pulsars are polarized and by how much gives us a clue into their emission mechanism. And by measuring Faraday rotation, or the rotation of this position angle with frequency, and also combining that with our knowledge of the dispersion measure, one can calculate magnetic fields, the line of sight magnetic field to all of these pulsars. And you can see the dispersion measures and rotation measures and magnetic fields in this table here. And this was the first plot of pulsar magnetic fields. The dark and light circles show different directions of the field. So you can see the magnetic field reversal in the galaxy, and the size of the actual amplitude of the magnetic field in that direction. So you can see, this result that there are, micro-Gauss fields in the Milky Way. And this was a really important paper because this kind of laid the framework for lots and lots of later work where we've really, we understand pulsar polarization much better now. We can measure magnetic fields along many, many lines of sight. And there were tons of papers like this. I picked this one to highlight, but lots of really core critical pulsar related work in those first few years with a 300-foot after pulsars were discovered. Okay. Green Bank Observatory also played a really important role in searching for pulsars. That happened a little bit later. This is a paper from 1985. The title of this paper was A Search for Low Luminosity Pulsars by Dewey et al. This was a survey called the Princeton NRAO Pulsar Survey. And you can see here the minimum detectable flux of this pulsar survey versus pulsar spin period. And what you'll see is that this was almost the most sensitive survey out there, although it didn't quite have sensitivity to millisecond pulsars. So at this time in 1985, when this paper was written, the first millisecond pulsar had been discovered. So 1937 plus 21 was found by Don Backer with Arecibo. It has a 1.5 millisecond period. This survey wasn't quite sensitive to that yet. It didn't have fast enough sampling time and fine enough channelization, but it was more sensitive than many and many other surveys at the time. And so it found a bunch of pulsars. This particular paper from 1985 announced 34 new pulsars. It also detected 49 known pulsars. You can see them on this ATOF plot. The stars are the new detections. One kind of interesting thing about this paper is, they look at the period distribution of pulsars, and they found that there's a falling off in period below a few hundred milliseconds, which is real. We do see, fewer pulsars here, and then a big, big question mark down here in this part of the diagram. So really at this time, back in the mid 1980s, we knew these recycled millisecond pulsars existed, but no idea how many there were. This was really a completely open field of research, which, as we'll see in later papers, Green Bank telescopes really played a very, very important role in. Okay, so moving on, 1986. So this paper that I'm highlighting here is by Jim Cordes, and he did some really nice early work on looking at pulsar dynamic spectra. So this is an image of a dynamic spectrum of a pulsar, and what this is showing is the intensity of the pulsar signal versus time and frequency. So this is radio frequency on this axis. This is time on this axis, and these contours show pulsar intensity. So the darker bits here, so here, 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 these are what we would call scintils. So this is constructive interference of radio waves traveling through the interstellar medium. These scintils have a characteristic frequency scale and a characteristic time scale. And this particular paper by Jim described how we can constrain pulsar velocities, this VISS, from the frequency scale and the time scale. So not surprising, if pulsars have higher velocities through the interstellar medium, they're going to have a shorter time scale variation in these dynamic spectra. This was a really important paper because it placed constraints on the number of pulsars with different transverse speeds. And so here's the histogram from this paper, and you can see the rough characteristic speeds of pulsars, a few hundred kilometers a second, a hint of a higher velocity population here, and a lower velocity population. This was important because it has a lot of implications for supernova physics, right? So what are the kick velocities that are imparted to pulsars in supernovae? Do you need like asymmetric neutrino emission? It's important for galactic kinematics. There's a ton of things that came out of this paper, and these are techniques that we still use today. Okay, let's move on through time. The next paper I picked is from 1990. And these words in green are the titles of these papers. I don't know if I pointed that out, but this paper from 1990 was by Foster and Backer. The title of the paper is Constructing a Pulsar Timing Array. This is a super important paper. This lays the groundwork for what we're doing with nanograv right now. This paper was very prescient, really. I mean, this was published back in 1990 before we really had the sensitivity to actually detect gravitational waves from supermassive black hole binaries. But they say here, arrival time data from a spatial array of millisecond pulsars can be used to search for a cosmic background of gravitational radiation. And so they use data on 3 millisecond pulsars to set limits on the cosmic background of gravitational waves due to supermassive black hole binaries, due to black holes at the cores of galaxies all throughout the universe that are slowly in the process of merging. And they also say analysis of data from several observatories around the globe will provide the best possible solution for these effects, which is what we are doing now. These are some of the plots from their paper. So this plot shows pulsar timing residuals. You see some more of these through this talk. So these are differences between when pulses from a pulsar arrive and when they're predicted to arrive based on a timing model, a model for all the astrophysical stuff that's happening to that pulsar. And just take a look at the scale of these. These are in microseconds. So you can see this y-axis scale is sort of tens to 100 microseconds, which is pretty good, you know, back in 1990. One thing I should mention is now, of course, this is after the collapse of the 300 foot. So for the next 10 years or so, the results I'll be talking about will be with the 140 foot or 43 meter telescope at Green Bank. Okay, so this was a super important paper and the start of a pulsar timing array program that has continued ever since this initial paper was published. And this pulsar timing array program that they started has now grown and expanded and become the timing program that we're carrying out with nanograv, but it's a continuation of this program. Okay, 1993. So back when I showed the list of the most highly cited papers with Green Bank Observatory telescopes, like right at the top were papers on neutron star masses. Neutron star mass measurements have been of a lot of interest, not only to astronomers, but to the fundamental physics community, and in particular, particle physicists who work on neutron star equations of state and really care about like what kind of exotic material could be at the core of a neutron star. And mass measurements really can constrain those equations of state. So this was a nice paper from 1993 that laid the groundwork for how we measure masses of neutron star systems in binaries. This was a paper by Steve Thorsett, where his group looked at 2 pulsars, and they measured an effect in these pulsars akin to the perihelion advance of Mercury. So the advance of periastron, or what we would call a mega dot. This is the longitude of periastron. They measured a change of this with time. This is a general relativistic effect. So combined with the classical mass function that we get from pulsar timing, this is just Kepler's laws. If you combine these two, then you can make a mass-mass diagram. This is the companion mass, the binary companion to this pulsar, which is a white dwarf, and the pulsar mass. This white region is the region that is allowed. This is a 68% confidence interval. So this region is the most favored region for both the pulsar mass and the companion mass. And of course, there's some uncertainty because we don't know the inclination of the orbit here. So that's why there's this broad line here. So this was a really important paper. It added 2 points to the neutron star mass diagram here. There had already been some precise masses measured for double neutron star systems, but this was a neutron star white dwarf binary. You can see that here, and here's another pulsar, a double neutron star system where the pulsar and companion masses were constrained in the same paper. And of course, we know now we have a much fuller picture of this diagram, but this was one of the first papers to use pulsar timing to weigh neutron stars with the 140 foot. Okay, So let's move on. 1994, there was a paper, this was Arzumanian et al. And they published timing solutions for 96 radio pulsars. Here are pulse profiles of some of the pulsars that they timed. These are slow pulsars. You can see their names. You can see the shapes of their profiles. They're quite diverse. And what they set out to measure was how noisy the timing of these pulsars are. And they did this by measuring a frequency second derivative. Came up with this metric, this delta metric for the kind of timing noise in pulsars, right? So how perfect is the rotation? So if there's no frequency second derivative, this is 0. If there's a large frequency second derivative, that means that there's quite a large wander in the frequency with time. They plotted that versus the period derivative and found this very strong evidence that pulsars with larger period derivatives that are spinning down more rapidly, these would be the younger pulsars, have higher amounts of this timing noise. This is a really important paper because timing noise is something that is really critical we think about for high precision timing, especially with nanograv now. And this sort of laid the groundwork to understanding that timing noise. It also has a lot of physics in it, right? So the amount of noise in a pulsar can tell us about the equation of state, just like the mass can. Okay, cool. So let's keep moving on. Kind of returning to the Crab, I thought it'd be fun to highlight some later work that was done with Green Bank telescopes and the Crab. In 1995, there was a nice paper by Scott Lundgren and collaborators using the 43 meter, where they observed giant pulses from the Crab Pulsar in the radio and correlated them with gamma ray photons, also from the Crab Pulsar. And you can see here on the left, here is a pulse profile of the Crab in radio. That's this darker line with these very narrow peaks. This is an infrared profile on top of it. And down here is an X-ray, this line here, and a gamma ray pulse profile. So it was around this time that there were, gamma ray and X-ray facilities that could observe a lot of pulsars. And this really opened up a lot of pulsar science, like trying to understand how radio emission relates to high energy emission. And the Crab is a great candidate for that because we can detect it across the whole electromagnetic spectrum. This is another plot from their paper. This shows the number of giant pulses versus their flux. This is a logarithmic plot, and so you can see this very long tail here. This is really interesting. So these are sort of super giant, very, very bright pulses. They found that the giant pulses are random. There's no real apparent correlation between the high energy photons and the radio flux. And this has a lot of implications for how we understand pulsar emission mechanisms. And kind of tells us that giant pulses are due to radio coherence, right? So increased coherence of radio photons and not overall just more plasma in the magnetosphere, because that would also result in more gamma ray photons as well. So this was a really important paper for understanding pulsar emission mechanisms. Okay, we're almost there. I think we're maybe half of the way, maybe almost 2/3 of the way through the, looking into the past bit. Another thing that Green Bank telescopes have played a very important role in is binary systems and, searching for effects due to planetary mass companions. Green Bank is a very sensitive telescope for pulsar timing. The 43 meter did a lot of really excellent pulsar timing work as well. So in 1999, there was a paper on a triple pulsar system in globular cluster in M4, and Green Bank telescopes have done a ton of really nice work on globular cluster pulsar timing in general. This is a really nice paper. So this shows on the left, these are residuals again. So these are differences between arrival times of pulses and when a model predicted they should arrive. And this top plot shows the residuals over about a decade. For this millisecond pulsar in this globular cluster. And this is what these residuals looked like, accounting for only a single companion, a white dwarf binary companion to this neutron star. Clearly, there's some unmodeled effect here, and it turns out that unmodeled effect is a planet. And fitting for a third object, actually a planet that's orbiting both the neutron star and the white dwarf with a very long orbital period, flattens these residuals. This is in milliseconds up here. This is in microseconds down here. So this really does a good job of fitting these residuals. this planet has a mass of sort of 0.01, 1% of a solar mass, and you can see that here. So this was really important. We had already known about a planetary system around a millisecond pulsar in the Milky Way, but this is one in a globular cluster. Lots of implications for like how pulsar astronomers search for these things, for how these kinds of planets may be captured or evolved with pulsar systems. Okay, cool. And this is kind of like a fanciful little cartoon of a pulsar with a planet orbiting it. Okay. Yeah, so looking also at like some more globular cluster science, Green Bank has done a ton of amazing things with globular clusters, and you'll see we've moved from the 43 meter to the GBT now. So this was a paper from 2005. This is by Scott Ransom and collaborators. This was huge at the time. So they found 21 millisecond pulsars in a singular globular cluster in Terzan 5. Here's an optical image of Terzan 5. Here are all the pulse profiles of these pulsars, and we name globular cluster pulsars very creatively, like A, B, C, D, E, F, G. You'll notice some of them are missing, like B's missing, because occasionally someone thinks they found a pulsar and then it ends up that pulsar doesn't pan out, and then that letter sort of goes away. So this was a really amazing paper based on many, many hours of observations with the GBT. And again, mass constraints come up in this paper. So this is one of these pulsars. This is another mass diagram based on a measure of this periastron advance. And you can see that the allowed region, it's this region here within these dotted lines, is much narrower, right? Because pulsar timing observations have become more and more sensitive. This is a bigger telescope, bigger bandwidth, better instrumentation, and you can see the probability distribution functions for the pulsar mass right here, sort of leading us to a mass of like 1.8 solar masses or so, which was pretty massive at the time. So this was a pretty important paper and a very useful new constraint on neutron star masses. Okay, 2006. So the double pulsar. So the double pulsar is the only system that has ever been found with two neutron stars in orbit around each other, where both the neutron stars have been detectable as radio pulsars. So this is a really important system for timing. Being able to time both of them gives us a mass ratio. That's this quantity R, which tells us exactly the ratio between these two masses. So when we make one of these mass, this is the companion mass, pulsar mass, in this case, they're both pulsars though, diagrams, we have this new constraint, which really allows us to like hone in on the masses much more precisely. So this system was found with the Parkes telescope in Australia, but Green Bank has done by far, most of the really precise timing on the system. It's a lot bigger than the Parkes telescope. So this shows the mass diagram from this paper. What these lines are different constraints on the masses that are set by different relativistic effects. So this is PV dot, the shrinkage of the orbit due to gravitational wave radiation. This is omega dot. We talked about that before. There are two parameters here related to Shapiro delay. So when the light from one pulsar travels through the gravitational well of the other pulsar, it's delayed. This parameter here accounts for time dilation and gravitational redshift. The amazing thing about this work is that all of these lines intersect in exactly the same point, right? So if general relativity wasn't correct, it would be a huge coincidence if they all predicted the same combination of masses, right? So each one of these measurements, there's an equation for it. Einstein predicted these effects a very long time ago, and they all depend on the masses of the pulsars. And these lines all intersect in a common point, meaning that general relativity is correct. It also means that we were able to constrain the masses of these pulsars to very, very, very high precision. This plot here in particular shows this Shapiro delay effect. So as one pulsar passes behind the other, we can see the residuals peak like this. So the signals arrive later and later as one pulsar passes behind the other due to this curved space-time around the companion. And this particular parameter is consistent with GR to 0.05%. So that's really amazing. This is the best strong field test of general relativity. Okay, another double pulsar thing. One other super cool thing that actually wasn't realized in the Parkes observations of the double pulsar, but was very apparent in the high sensitivity Green Bank telescope observations, is that if we look at the eclipse of pulsar A, so this shows the pulsed flux of A. A is the brighter recycled millisecond pulsar in the system versus orbital phase. You can see that that flux decreases and increases again, and we would call this an eclipse. So as A passes behind B, its radio photons are absorbed in the magnetosphere of B. We see an eclipse. But what Green Bank telescope data showed was that this eclipse was not monotonic. The emission didn't go to zero and then come up again. There were transparency windows. So you can see throughout this eclipse, there's bright emission, almost as bright as outside the eclipse, every once in a while. And every once in a while is not just random. It's at exactly half the spin period of B. This is super cool. So what we think is happening here is that the emission from the A pulsar is getting absorbed in the B pulsar's magnetosphere, but as B rotates, there are regions where the emission can pass almost all the way through, and other regions when it's completely absorbed, right? And it turns out there's much more absorption like above the polar caps, where there's a lot more plasma than when you're sort of like passing close to the side of this magnetosphere. So this is really awesome. And the other amazing thing about this is by looking at the evolution of these transparency windows, we were able to constrain the geodetic precession rate of B. So B's beam is precessing with time with a period of about 75 years. This is a relativistic effect. And we could show that this was consistent with GR to about 13%. So this was an amazing test of general relativity, as well as just a super cool physical effect that no one had seen before. Okay, moving on. So 2009, this was a really important result coming out of the Green Bank telescope. The title of this paper was a radio pulsar X-ray binary link. So for many years, it had been theorized that millisecond pulsars got their very fast millisecond periods through accretion of matter and angular momentum from a companion star, right? And that explains why most of them were in binaries, why they were so stable, why they were rotating so rapidly, but we didn't have any direct evidence for that until 2009, when this system called 1023 plus 09 was discovered. And if you look at this plot over here, this shows pulse phase. So this is like the pulse profile. There's a double peaked pulse profile versus orbital phase. Not all of this data is with the GBT. Some of this is with other telescopes as well. But this is the GBT data here, for instance, this is 1100 to 1900 plot. You can see that the pulsar disappears for large parts of the orbit, much more so at lower frequencies and less so at higher frequencies. We also see big changes in dispersion measure. So all this stuff implies that this is a really messy system. There's a lot of gas that's still in the system, even though we're seeing radio emission. And looking at optical observations of the companion to this system, it was very clear that there was evidence for recent accretion, right? So this was proof of this recycling hypothesis for millisecond pulsar formation. It showed that there was recent accretion in this system, and that indeed this millisecond pulsars are, born through accretion of material from a companion star. After this paper, we realized that this particular pulsar goes through periods where it's not detectable in the radio and it's detectable as a low mass X-ray binary pulsar. And so it goes on and off between actively accreting and getting spun up, and then the accretion stops. It's able to detect it as a radio pulsar again. And we know a few other cases like this now, but this was kind of really an important moment in understanding millisecond pulsar formation. Okay, and I think we're almost there. I'm spending more time on the past stuff. It's just really fun to talk about these things, and I think I'm going to be whizzing through the present and future, but that's okay. I think we're almost done with the past stuff. So this paper is the #1 most cited pulsar paper with the GBT. I'm not sure if it's the #1 most cited paper period with Green Bank, and maybe I should have looked into it, but this is an extremely well cited paper that presented mass constraints on a millisecond pulsar using the Shapiro delay effect again, where this signal arrives later when the pulsar passes behind its companion. This shows the full signal. These two plots here, these are residuals when you fit for other stuff, but not the Shapiro delay effect. And this is when the Shapiro delay effect is fit for. And the outcome of this are constraints on the companion mass, the inclination angle, and the pulsar mass. And this is really important. So the Shapiro delay signal, unlike that omega dot we talked about before, actually gives you a constraint on the inclination angle, which allows you to get a much better constraint on the pulsar mass. And so this pulsar mass is around 2 solar masses. This was really exciting because this rules out a whole bunch of equations of state for neutron star material. It rules out most of the more exotic ones, the ones that have hadrons or quarks or things other than neutrons. And so that kind of, it was very interesting to particle physicists at the time. As you know, this is still a really interesting field. We'll come back to one more pulsar mass measurement. Before we do that, just a little bit about pulsar searches with the GBT. In 2014, we published the first paper about a survey, which is still going on now. It's almost complete, called the Green Bank Northern Celestial Cap Pulsar Survey. This is kind of a misnomer because it's become a survey of the entire sky visible to Green Bank now. This plot here shows the sensitivity of this survey. It's a low frequency survey. That's great for detecting faint pulsars. There's only one pulsar survey going on right now that's actually more sensitive than it. And the Green Bank survey is even a little bit more sensitive for the very shortest period objects. So this is the best survey in the world for detecting very short period millisecond pulsars. This first paper announced the discovery of 62 pulsars. You can see some of the profiles here at different frequencies. These again are timing residuals. I'm just showing this to illustrate that some of these pulsars, like this one here, this 0645, are extremely precise timers and have actually been added to this pulsar timing array for gravitational wave detection that Foster and Backer talked about. So a number of our nanograph pulsars that we're observing now have been found in this GBNCC survey. This survey is currently at 195 pulsars, and 33 of them are millisecond pulsars. Okay, another pulsar mass measurement. So in 2020, another 2 solar mass pulsar was published. This is 0740 is the name of this pulsar. This was published using, well, the analysis was done using nanograph data, supplemented with data taken on this pulsar right at superior conjunction when it was behind its white dwarf companion to really sample the Shapiro delay signal better. You can see the mass constraints on this system. And if you look at the peak of this PDF in pulsar mass, you can see that it's even higher than 2 solar masses. So this was very exciting to the community. This was the highest neutron star mass ever found. And this is also, this is Green Bank telescope, very sensitive GBT observations that made this possible. Okay, and I think this is the last, yes, this is the last sort of history one. Coming back to the double pulsar, and I'd like to kind of like, come back to things like the Crab mass measurements, this double pulsar, just to really illustrate the importance for pulsar timing of accumulating like very long baselines of pulsar timing data. The longer we observe a pulsar, the longer we can accumulate data, the more sensitive we become, right? There's never a time where we want to say on a system like the double pulsar or 0740, we have enough, let's just stop there. The more we observe, the more sensitive we're going to be. So in 2021, we published another paper on the double pulsar. This left plot here shows timing residuals for a bunch of different telescopes that were looking at the double pulsar. And the reason I'm showing this is you can see Nancy in France, Parkes in Australia, and here's the GBT at the 2 frequencies we observe the GBT with. And you can look at the y-axis scale and just see that our GBT residuals are much smaller than the Parkes and Nancy residuals. This is due to the larger collecting area, of course, and also due to the wide bandwidths and sensitivity of the backends that we have. So the GBT has provided by far most of the sensitivity to this double pulsar experiment over the past 15 years. And this is a really exciting, just beautiful plot. This shows the shift in periastron time. So this is related to the loss of energy from the system due to the emission of gravitational waves. The blue points are measurements, and this red line is what is predicted by general relativity. And you can see that there is a perfect match of our measurements with what GR predicts. And this is a match at less than 0.01% precision. So this is the best test ever of gravity in the strong field regime. This is the updated mass diagram. So this is pretty impressive if you think back to the one that we saw in the 2006 paper. These lines were not lines, they were bands. These are still bands, but they're so precisely determined that they just look like lines, right? The errors on these parameters are extremely small. we can pinpoint the masses of these pulsars down to 4 significant digits after the decimal place. So these are incredibly precisely determined neutron star masses, and a very, very precise test of GR. There's a new band on this diagram that wasn't on the one in 2006, and that is this geodetic precession result from that Breton et al. Paper from that eclipse work. So that provides another constraint on this mass plot. Okay, so I spent a lot of time on the past. Let me spend just a little bit of time talking about the present. Because I don't have much time, I'm just going to focus solely on what we're doing with nanograv, because I purposely didn't really highlight any gravitational wave detection stuff aside from that original Foster and Backer paper and the other papers. So nanograv is a collaboration. We've been using the GBT for about 17 years now to time pulsars, to form this pulsar timing array, to look for low frequency gravitational waves. We're part of a bigger international collaboration called the International Pulsar Timing Array. The big picture of what we're trying to do is we want to detect gravitational waves that have very long periods, right? So periods of like decades. And we want to do this in order to, not study the pulsars themselves, but detect very, very massive black holes at the cores of merging galaxies. So if we look at like the picture of galaxy growth and evolution through cosmic time, and we can see that galaxies used to be, the very early stages of the universe when galaxies were first formed. They were small, very irregularly shaped. And then with time, galaxies have grown larger. They've grown more structured. And we think this has happened through the process of mergers. And you can see that electromagnetically, we see galaxies that look like this, where 2 galaxies are clearly coming together. But there's lots of questions about the final stages of this process, and we call this the final parsec problem. So how do these 2 black holes at the core of this merger get close enough together to be driven to very close separations by gravitational waves? And there's lots of uncertainties about the physics of this process. How important are things like stars and gas? How long does the process take? And we can't answer this electromagnetically because these black holes are so close together, we can't resolve them with telescopes. The only way to probe this process is with gravitational waves. And so that's what nanograv is trying to do, detect these very low frequency waves that will allow us to probe the merger history of the universe. So a little bit more about pulsar timing arrays. The idea is that, we're here on Earth, we're observing a network of pulsars distributed throughout the Milky Way. The arrival times of the pulses from all these pulsars will be affected by gravitational waves. The perturbations are going to have 2 terms. There'll be an Earth term due to the effect of the gravitational wave on the Earth at the moment we receive that radio pulse. And there'll be a pulsar term due to the effect of the gravitational wave on the pulsar at the time that pulse left the pulsar. So we can look for specific correlations in arrival times from all of the pulsars in the array that are exactly what we expect due to quadrupolar gravitational wave perturbations. We can search for different types of sources. We can look for a stochastic background. So that's the sum of the gravitational waves from all of these merging supermassive black hole binaries all throughout the universe. And we can also look for individual supermassive black hole binary sources. We're currently observing around 70 pulsars, a wide range of frequencies. That wide frequency range is really important so we can correct for dispersive effects due to the interstellar medium. We've been very fortunate to get funding from the Moore Foundation and from NSF to purchase time on the GBT for this experiment. We're also using CHIME. We were using Arecibo, of course, that provided about half our sensitivity until it's collapsed. And we've been really lucky to be able to increase our GBT usage to at least partially compensate for the loss of Arecibo. We also have small programs with the VLA and with the FAST telescope in China. I'm just going to move through this really quickly. So what we do when we time pulsars is we measure a time of arrival at every epoch of observation. We get that by adding up all the data, all of the pulses on a particular epoch, excuse me, sorry, to form an integrated profile. And then we compare that time of arrival at one epoch with that predicted by a model, and we calculate a residual, right? So this is what we've been talking about, the difference between our model predicted and measured times. To do this, we need to model all the astrophysical stuff happening in a pulsar system things like the position, the proper motion, spin frequency, binary parameters. And I'm just going to whiz through these because I don't have much time. The way Nanograv works is we release data every couple years. Our last release had 47 pulsars in it. That was our 12.5-year release. We are working on our 15-year data release. It will be out imminently, sometime over the next, we hope, like 6 months or so. That'll have 67 pulsars. Here are some of the pulse profiles and polarization profiles from this release. I thought these would be fun to include just to compare with those like Manchester et al. Profiles that we saw earlier. You can see how far that like pulsar science has come in that time. So as I said, we're sensitive to very low frequency gravitational waves, and this is because we're analyzing decades of data. So we're most sensitive at like 1/, our data set length, which is like 10 to the -8, 10 to the -9 hertz. LIGO sensitive way up here, tens to hundreds of hertz, and we're down here. We're sensitive to gravitational wave strains of around like 10 to the -15. And you can kind of understand that by looking at our residual RMS. It's a couple hundred nanoseconds on average over the time span of our experiment. And that gets you that sort of rough characteristic strain sensitivity. We analyze residuals that look like this. These are examples for 3 pulsars. I don't have any time to talk about them, but if you look at the y-axis, you can again see how far we have come. The plots that we saw earlier had scales of like tens to hundreds of microseconds, and these are sub-microsecond residuals. Okay. We also do this with international pulsar timing array data. We combine our data with European, Australian, Indian colleagues. These are some residuals from our last IPTA release. I am going to just scroll through this really quickly. There's lots of different sources of noise we need to model. We can do that. They look different from gravitational waves. Sorry. This is the signature we're looking for in our data. We're looking for this very specific correlation in arrival times versus pulsar angular separation. This is predicted by general relativity. There's a dip at around 90 degrees, an anti-correlation, and a positive correlation around 0 and 180. One really important point is you'll see the peak is at 0.5. And this is because we're only looking for the Earth term of this correlation. The pulsars are all at different distances. These gravitational waves will be completely uncorrelated at the pulsars because we don't know the distances to the pulsars well enough. So when we do detect gravitational waves through this Hellings and Downs correlation, we're going to be detecting the effect of gravitational waves on the Earth itself, which is pretty cool. So where are we now? And I'm going to go very quickly through this. In our last data set, we detected a source of common noise in our data. We can't say for sure it's gravitational waves, but what this left plot shows is the probability density for a common noise process versus the gravitational wave amplitude, if this process is indeed gravitational waves. And you can see that these PDFs peak at a particular gravitational wave amplitude. These two different curves are doing different things with the solar system ephemerides. It doesn't matter, they're very consistent. This just shows this isn't an artifact of having an incorrect solar system ephemeris. So this is very exciting. This shows that there's a common noise process in the data. All of the pulsars see this same noise process with a similar spectrum and amplitude. We can't make it go away no matter what we do. We cannot make this noise process go away. However, in our last data set, we did not yet see the quadrupolar correlations that we need to see, this clear Hellings and Downs curve to say that for sure it's gravitational waves. This shows the correlated amplitude versus angular separation. And this blue dotted line is the best fit Hellings and Downs curve. And you can clearly see that these points, these black points are our bin data. They're not matching this Hellings and Downs curve perfectly. So we cannot yet say these are gravitational waves. We can say what we do see is consistent with gravitational waves from a population of supermassive black hole binaries. So that's very exciting. If we look at this spectrum of this signal, it has a very red spectrum. There's a lot more power at low frequencies. That is what we expect. These gray kind of violin shaped things here, these are the power at different frequencies. There's a lot more power at low frequencies. It has roughly the power law index we expect. That's this dotted line. Due to supermassive black hole binaries, these two contours here show our estimated power law index, and it's consistent with supermassive black hole binaries. So this is really exciting. We can't say it's it for sure, but it's certainly consistent. It's also consistent with some more exotic stuff like gravitational waves left over from the Big Bang. gravitational waves from cosmic strings. We just really can't discriminate these yet, although we think the most likely source is these supermassive black hole binaries. We see the same thing in data from the International Pulsar Timing Array when we combine data from different collaborations, and independently in the EPTA, the European Pulsar Timing Array data, and the PPTA, the Parkes Pulsar Timing Array or Australian collaboration data. And all of the data is consistent amplitude, consistent spectral index for this common process. So that is very exciting and very encouraging. We predict that if this is indeed a gravitational wave signal, we should detect it with high significance in our next data set. So with a signal to noise of something like 4 to 7. In the 15-year data set, which we are working on currently, this is a simulated curve. This is what we might expect to see in our 15-year data set. We should start to tease out these Hellings and Downs correlations, which will tell us that for sure these are gravitational waves. So it's very exciting. We're probably 6 months out from publishing these results. It's really tricky because we're trying to coordinate with our international colleagues. And so it's hard to make an exact estimate, but we're close. I'm going to just skip through these single source slides. I can answer questions about them later. Just a little bit about the future of Green Bank in particular and what it can do for pulsar astronomy. And I've kind of focused these last future slides on nanograv and what nanograv's goals are and how they relate to the GBT. One of our big goals over the next decade is to increase the number of millisecond pulsars that we're timing. So our gravitational wave sensitivity is linearly dependent on the number of pulsars. If we double the number of pulsars in our array, we double our sensitivity. So we really want to add more pulsars. We also want more uniform sky coverage of millisecond pulsars. We have some holes where we don't have a lot of pulsars, don't have a lot of sensitivity. So searches for pulsars are really critical. This is a way that we involve a lot of students, high school and undergraduate students, in helping us look for pulsars through this Pulsar Search Collaboratory, now Pulsar Science Collaboratory. So this is a really nice way to involve students. We're super excited about the Wideband Receiver. This is a first light plot. I think Ryan Lynch is responsible for this, showing the amazing wide bandwidth that we will be able to have access to with the Wideband Receiver. And these orange boxes are what we have access to now. And so you can see just by looking at this, we're using 2 separate receivers, the 800 megahertz and L-band receivers. This is going to be really transformative for nanograv work. We're going to get a lot more sensitivity just from the wider band. We'll increase our observing efficiency because we'll be able to not observe twice with 2 separate receivers, but get everything in one go, and we'll be much better able to track interstellar medium delays. So we're very excited about this. There's another really cool program on the GBT right now to try to mitigate delays due to scattering through a technique called Cyclic Spectroscopy. And this is a technique that allows us to deconvolve a scattered signal due to the interstellar medium from the intrinsic pulsar signal. And so this is an effort that's funded by the NSF. It's being led by Ryan Lynch. This plot on the left shows a pulsar signal that is scattered, this black signal. And the red signal is the deconvolved signal with the scattering removed. And this technique of cyclic spectroscopy will allow us to do this. We'll be able to get much higher resolution dynamic spectra. And most importantly, some millisecond pulsars that right now aren't good enough timers, aren't what we would call pulsar timing array quality, will be pulsar timing array quality with this technique and with the ultra wideband receiver. So that's super exciting. This should allow us to add more pulsars to our array that currently just aren't sufficiently well timed to be able to do that. We're also working on incorporating chime data along with the GBT data. This is really exciting. We observe with the GBT only monthly, chime observes daily. So this is very complementary to the cadence of observations we have with the GBT. It's not clear yet exactly how many pulsars we'll be able to time well enough with chime and exactly what the improvement will be, but we're working really hard on incorporating this data into our data set. Finally, we're really pushing hard on the IPTA, trying to include data from more countries. We have an NSF award that's funding a project manager for the IPTA and a cyber infrastructure specialist, which should really help provide the organizational and computational infrastructure we need to really make this project work and develop international data releases faster and that are much more sensitive. And so the IPTA really, I think, is the way of the future. Another 5 or 10 years down the line, I hope we're not talking about our individual PTA releases as much as this uber international data set. And I'm sorry I've gone on so long, but I will just leave this up for now, and I'll just end by saying I really hope we can bring on another 65 years of pulsar science with Green Bank, because the last, well, not 65, we didn't know about pulsar 65 years ago, but the last 55 years have been very, very exciting. So thanks very much, Jesse, and thanks everyone for listening.
Wow,
I'm sorry I had
thank
to
you very
skip over
much.
stuff, but I'm happy to take questions later, even after this session, if people want to like email me or whatever.
Absolutely. And as a quick reminder, everyone, you can find all of our talks shortly after they've premiered on the Green Bank Observatory YouTube channel. There is a separate playlist for the 65th anniversary talks. But if people are willing to stick around for a little while longer, we can go through and answer some questions. And we already have a few in the chat, so I'll read those out. In the meantime, if anyone wants to ask a question directly, feel free to raise your hand. So the first question is, have there been further analysis of pulsar hotspots, such as the ones identified in J0030 plus 0451 by the NICER observations?
Yeah, so this is a really interesting question. So for those of you who might not be familiar, NICER is an X-ray telescope, which is observing a sample of MSPs and trying to map the thermal emission from millisecond pulsars in order to tell which parts of the surface are hotter than others. And it's been really interesting because the picture is more complex than we originally thought. There's very kind of complex morphology to these hotspots where they don't look like. So I'm trying to answer this without making it too complicated. Anyway, we can learn a lot about pulsar emission from looking at like the temperature of the surface of the neutron star being mapped by these X-ray telescopes. But I'm not part of this project, so I don't know that I have a good answer as to like unpublished NICER results. You know, I think this is one thing I will say is I know they're looking at several MSPs. They have very precise estimates of the radius of these MSPs, and taking the radii measured by NICER and combining that with masses measured with the Green Bank telescope. This pulsar here in particular is one of our nanograph pulsars. We can get really good constraints on the moment of inertia of the neutron star and also on equations of state, which is pretty exciting because we only get the one piece, the mass, from pulsar timing, and NICER will give us this other piece, the radius, through mapping this thermal emission.
All right, brilliant. And actually, there's a question before that I missed. Is there an example of a pulsar orbiting a black hole of any mass?
Not yet. This is one of sort of like the holy grails of pulsar searching. They should be out there. There should be neutron star black hole binaries. We know they are. We've seen them merge with LIGO. So far, we have not detected any, at least that we know about. It's possible a pulsar that we've already discovered is in a very long period orbit with an unseen black hole. And the only way that we will know is, you know, to accumulate a much longer timing baseline. So we could search for very kind of long perturbations. But as far as we know, right now, none of our pulsars are in orbits around black hole.
So you believe with the current instruments available to us, it is possible to detect?
It is possible. And if you look at like population simulations, right? So like how many pulsar black hole binaries there should be for every pulsar neutron star binary, we should have about one. Like we should be kind of, you know, detecting one about now. So yeah, I'm pretty hopeful that in my lifetime, at least, we'll finally find one of these systems.
It's only a matter of time.
Yep.
All right, the next question is, have any significant data releases from FAST of the new pulsar discoveries revealed any new or unusual or interesting properties of these pulsars?
What a great question. Yeah, so gosh, yeah, so I don't know. I can't say that I'm totally up to date on every single FAST paper. So far, I mean, they found a ton of pulsars. They found a bunch of millisecond pulsars. They found a couple double neutron stars. They found some eclipsing binaries. I'm not aware of anything that's like totally turned stuff on its head. One thing I'll mention while we're talking about FAST is there is some follow-up of fast pulsars being done with the GBT. So that's really great. A grad student of mine named Victoria actually is working on observing a double neutron star system with the GBT that was found with FAST, an eclipsing pulsar binary system, and some kind of longer period like sporadic pulsars with the GBT. So the GBT is contributing to this. And I might be wrong. Like I hate saying like nothing completely new or unusual has come out, but not that I'm aware of.
Still a great example of observatory collaboration.
Yep.
All right. And then if you were to normalize the measured correlation so that it spanned from -1 to +1, what is the value of the correlation coefficient of the monopole detection?
Oh, Anish, I was hoping to avoid any discussion of the monopole detection. So are you talking about like, yeah, do you mean the monopole detection in our current like nanograph data set? Is that what you mean, Anish?
Yeah, yes, that's right. Yeah, so you said the predicted correlation in coefficients is 0 to 0.5.
Yes.
Right. So what is the value for the monopole? That's what in the current detection, what we are.
Yeah, I don't want to talk about our current data set
Okay.
because we're still working it out. Yeah, so we do see sort of like a non-spatially correlated source of noise among all the pulsars, and we are trying to tease out what that might be. It could be something like a clock or something like that, but yeah, I don't want to discuss it. I can discuss it privately with you, Anish, but it's so complex and so complicated, and I also don't want to say anything I'm not supposed to say because we're not really talking about the new data set yet.
Okay.
Future results to follow.
Yeah, results to follow. It's interesting, but.
All right, and in the interest of time, I'm just going to go with one final question. This one from the GBO director himself, Jim Jackson. If you could have any future instrument you want on the GBT, what would it be?
Oh, Lord. Yeah. Well, I would have said an ultra wideband receiver a couple of years ago. I think for nanograph science, that is by far the most transformative thing that we can do, but we already have it, and it doesn't need to be any wider band. Like it really is what's up there now is has just the right range of frequencies for pulsar timing. Wish it had a little bit lower system temperature, but hopefully that will come. So we already have that. The other, big instrument that I didn't talk about at all are instruments for pulsar searching. So phased array feeds that can cover a very large area of the sky at once. I think that's something that could be really transformative for pulsar searching. So something that's capable of forming like many phased array beams to cover, a very large portion of the sky all at once for both pulsar and fast radio burst searching. I would say that.
An excellent answer. All right. Well, since we are a little bit over time, if you have any further questions for Maura, feel free to get in touch with her. But otherwise, let's give a warm virtual round of applause to Dr. Maura McLaughlin one more time. And thank you all very much for attending. Please join us next week, both virtually and in person, for a discussion on astrochemistry at the GBO by Dr. Brett McGuire. Thank you all very much for attending.
Thank you.
Thanks, Jesse.